Hello everyone. In this video, we will discuss about sampling distribution and sample from a normal population, and then a very important concept, central limit theorem and problem based on that. So let us start with first understand what is sampling distribution. So before that, we have to know what is statistics. So in sampling, there are two things. One is population and other one is sample. So the estimates which are based on population, they are known as parameters, whereas the estimates which are based on sample, they are called as statistic. So for example, sample mean is calculated by samples. So it is a statistic. Sample standard deviation or sample variance is estimated by using samples. So it is a statistic. So a statistic is a number obtained from random samples taken from a population. And since a sample is a random, so every statistic is a random variable. And this means that a random sample is a random variable and each unit of it have a probability distribution as a population. So because we are drawing these samples x1, x2, x3, x4 and so on, xn from a population. So each of these units will follow the same distribution as of population. And that means whenever we form an statistics such as sample mean, it has also a distribution. That is basically called a sampling distribution. So the probability distribution of a statistic is called its sampling distribution. Let us now see what is the meaning of sampling from a normal population. So when we are drawing a sample of size n, x1, x2, x3 up to xn, be an IID, independent and identically distributed random sample drawn from a normal population which have a mean mu and variance sigma square. So that means here your population X is following normal distribution which has mean mu and variance sigma square. So we know that any linear combination of sample unit will also be normal. Okay, so here this sample mean is used, well known, and it is a very famous statistic used to estimate population parameter, which is mean. And second one is sample variance. So to understand what is the sampling distribution and how it can be formed or obtained, we need to find out the distribution of sample mean. That means when x, that the population follow normal with these two parameters mu and sigma square, what the distribution your sample mean x bar will follow. So what kind of distribution with which parameters this x bar will follow, we need to compute. Before that, let us see the definition of sample mean and sample variance. So sample mean is defined as usual. We all know that what is the meaning of the mean, but it is defined in terms of sample units. So if I have a sample of size n and which is taken from a normal population which have mean mu and variance sigma square, then sample mean denoted by x bar, and it is defined as sum of these uh, samples x3 plus x4 and so on plus xn and divide by n. This I can write as summation xi I equal to 1 to n divide by n. So this is your sample means as usually defined, or it is well known. So our task is to find now what is the distribution of x bar. Definitely, because x bar is defined as a sum of these random sample, and these random samples are taken from the normal. So this means that X bar will also follow normal, but with what parameters? What is the mean and what is the variance we have to compute? Okay, so this is, and this IID is the very meaningful word here. Its full form is independent and identically distributed. So this means that whenever we are drawing a sample from a normal population, each sample unit will have same distribution as of the population. So this means each of the xi have mean as of population, which is mu, and each of unit xi have same variance as the population, which have sigma square, so it has also sigma square. So this will be used, and each xi, x1, x2 and xn all are independent. So these three are the characteristics which are need to be understood before going ahead. So this is how sample mean is defined. Now sample variance is another statistics, and it is defined as S square is equal to 1 upon n minus 1 summation I equal to 1 to n, and the difference of xi minus with the mean of that is sample mean and squared it. So this is also the standard definition as sample variance, and very interesting, this is unbiased estimator of population variance, which is sigma square, and this X bar is also unbiased estimator of population mean. What is the meaning of estimator? Whenever any statistic is used to estimate some characteristic of population, it is known as estimator. There are many statistics which are not used to estimate any population parameter. So in general, this sample mean is used to estimate population mean, and sample variance as a square is used to estimate population variance. So these two are the well-known statistic, or you can say estimator in the sampling theory. So let us move to our original question. What is the distribution of sample mean? We will cover this. So for this, we already understand the distribution of sample mean is normal, but with what parameters? So we compute mean of x bar and variance of x bar. So let us compute here. It's very easy to compute. So E of x bar we need to compute. So by definition, expectation of x bar means x1 plus x2 plus x3 plus and so on plus xn divided by n. This is by definition, as x bar is defined as follows. So now using the expectation property, I have 1 upon n outside, and this expectation of sum of two random variable will be expectation of individual. So I can take this expectation inside as individually. So E of x2 and plus E of x3 and plus and so on plus E of xn. Now, as I said, the property is that each of these units will have same population, same distribution as the population distribution. So population distribution is normal. So 1 upon n, and each will have same mean as of the population, which is mu. So mu here plus E of x2 is mu plus E of x3 is mu plus and so on. E of xn is also mu. So what we got from here? We got 1 upon n into n times, because this sample is of size n. So this summation will lead to n. So n times mu. So this n cancel out. I have mu. So what is interesting result here? Expectation of sample mean is same as the population mean. And this is the property that X bar is unbiased estimator of population parameter mu. Now same we can find the variance of X bar. So let us find what is the definition of X bar and apply on the mean. So it is defined as whereof I can write summation xi upon n. And this I can further write as 1 upon n square and then into variance of individual xi. So whereof x1 plus whereof x2 plus and so on plus whereof xn. Now, what is the variance of, and one more important thing here, whenever we are taking variance of two random variables as sum, so variance of x1 plus x2 is variance of x1 plus variance of x2, plus there is some additional term which is called covariance between these two variables. But because here each unit is independent, so covariance is zero here. So that's why here there is no covariance term because each x1, x2, x3 is independent. So I can write now 1 upon n square into variance of x1 is sigma square plus variance of x2 is also sigma square plus variance of x3 is sigma square plus and so on. Variance of xn is also sigma square and these are added as n times. So I have now 1 upon n square into n times sigma square. So finally I got here this sigma square by n. So this is actually variance of x bar. Sigma square by n is variance of x bar. So ultimately what we got is we have a distribution of x bar, that is sample mean, it is follow normal with mean as same as population, that is mu, and variance which is not the same as population but divide by n. So sigma square by n. So this is the distribution of sample mean. Now let us understand the, because it is x bar is following normal distribution, so we can change this x bar into standard normal variate. So here is the normal curve I am showing again here. We have shown this in previous video on the normal distribution, because we will use here again for computing the probabilities of sample mean lying from certain range, let's say A to B. So here I am repeating again here. So this is the normal curve and this x-axis is now here sample mean and y-axis represent the probabilities, and that's why the curve will not never lie below the x-axis. And this is the mean here, x is equal to mu, x bar is equal to mu actually, because it has same mean as the population, and this green color shows 1 sigma range which is 68% and its exact value is 0.6826. So this 68% around area is added here, and this right side is 34% and left side is around 34%. And if I go this next color here, it is 2 sigma. So 2 sigma range is 0.95. So this is 0.9544. So this 95% around the total area from here to here, the area under this curve above the x-axis, that means this total from here to here and below this curve is 95%. And if I go the next standard deviation or 3 sigma range, so it is 99.73% around, which is we call 3 sigma. So this is the largest sigma, which is 3 sigma here, and its total area is 99% around. So very few of very small region lying outside these 3 sigma ranges. So we will compute these probabilities, and we can see here the curve is symmetric about this mean. So the left side area is 50%, right side area is 50%, and total area under curve is 100%, that is 1. Now let us move to uh, understand what we have covered so far, and then we'll move to a very important theorem. So we have seen that we have a population here, and it has the parameters mean as mu and variance as sigma square, and we have drawn a sample from here in this population, which is x1, x2, x3, x4, and so on xn, and this the sample here. So what is this uh, uh, mean? We are computing here x bar as following normal with mean mu and variance sigma square by n. And here x is following normal with mean mu and variance sigma square. So here are the properties of this sample mean. So here mean equal to mu, and variance of x bar equal to sigma square by n. So there is one concept here that we call standard deviation, or it is called standard error. So standard error is equal to sigma by root n, because variance is sigma square by n. So I have to take positive square root, which is sigma by root n. So this is the well-known term, shortly denoted by SE, standard error. And this is mu of this mean of this sample mean. So with this understanding, let us approach to a well-known theorem, which is called central limit theorem here. And this state whatever we have covered so far. So this theorem statement is it gives the distribution of sample mean when sample is drawn from a population which is not necessarily normal. So far we have seen if population is normal, the sample mean distribution is normal. But central limit theorem says whether population is normal distribution or not normal distribution, if I draw a sample which is sufficiently large, then the sample mean x bar is approximately normal with mean mu and variance sigma square by n. And this large sample mean is n is greater or equal to 30. And if n is less than 30, we call it small sample. Small sample. N is greater than 30 means large sample. So this theorem states that if you have a given population as normally distributed, then it will not matter the sample size, because we have already seen the distribution of sample mean is normal if population is normal. And this means when x is normal with mean mu and variance sigma square, this implies x bar will be normal with mean mu and variance sigma square by n. But if x, the population is some other distribution not normal with mean mu and variance sigma square, this means the sample mean will be normal with mean mu and variance sigma square by n if n is greater or equal to 30. That is large sample. And if population is normal here, then this will follow. And if population is any other distribution rather than normal, the sample size should be drawn large, that is greater than or equal to 30. So this is the central limit theorem, and because x bar is normally distributed here in both the cases, so now I can change this x bar into z, which is standard normal variate, so that we can find the required probabilities. So this z equal to x bar minus mean of x bar divided by standard error of x bar, which is sigma by root n. This will follow normal distribution with the mean 0 and variance 1. And that's why we have shown this curve here, just to find the probabilities. So again here, if you see, these points are z equal to 0 and this z equal to 1 here, and this point is z equal to 2 here, and the last point is z equal to 3 sigma, and this side we have z equal to -1, and here I have z equal to -2, and this I have z equal to -3. So whether we write x bar equal to mu or we write z equal to 0, both have same meaning. So I hope you understand central limit theorem. It has only 2 points that I explained here. Now this can be seen by a grammatic representation here. So this shows distribution of sample mean will be normal if sample size is large enough. And so here this curve represents that distribution is not normal. So it will not matter if sample is sufficiently large. It will automatically be taken as normal distribution, and this large sample means n is greater than or equal to 30. This will be used also when you use the testing of hypothesis for large sample and for small sample. So for large sample we have Z test, which is very similar as we are doing the central limit theorem. So let us move to the problems, and here is problem 1. So this statement is a numerical population of grade point averages at colleges has mean 2.61 as standard deviation 0.5. If a random sample of size 100 is taken from this population, what is the probability that sample mean will be between 2.51 and 2.71? So you can see here at no place it is given as the population is normal. But what is given as, you have a sample of size 100, so n is equal to 100, which is greater than 30 actually, and this means large sample is given. And what is rest given? The average grade point at college has mean mu is equal to 2.61, and standard deviation of the population, that means sigma, is given as 0.5, and sample size 100. So what is the probability? You have to find the probability that sample mean, which is x bar, will lie upper limit is 2.71, lower limit is 2.51. So this you have to obtain. So as I said, because sample size is large, we can apply central limit theorem. So let us write here. So as n is greater or equal to 30, this implies we can use central limit theorem. And what central limit theorem says? X bar will follow normal distribution with mean mu and variance sigma square by n. And this means E of x bar is equal to mu, which is 0. Not 0 point, it is 2.61. 2.61. What is the standard deviation or standard error of x bar? Sigma by root n, which is 0.5 by root of 100. So this value is given as 0. How it will come? There will be 10. So 0.05. Now finding the probability of x bar in this range, I have to change this x1 bar, x2 bar into z1 and z2. So the probability of finding x bar from these two ranges will be changed to probability of finding z between z1 and z2, which are corresponding values for x1 bar and x2 bar. So this we have to find out. So let us do some calculation here. So when x bar equal to 2.51, what is z1, which is x1 bar minus e of x1 e of x, that is mean of the sample mean, and then a standard error of x bar. This is sometimes written as, in general, we are writing x minus bar minus mu of x bar divided by sigma of x bar in some notation in textbook. So this is the mean of sample mean, sigma of sample mean. So this we can write now 2.51 minus 2.61 divided by 0.05, which is minus times 2. Now for Z2, what we have? X2 bar equal to 2.71. So what is Z2? X2 minus mu of x bar divided by sigma of x bar. So this is equal to 2.71 minus 2.61 divided by 0.05, which is 2. So this means probability that 2.51 less or equal to x bar less or equal to 2.71 is now changed to probability of finding between minus 2 less than or equal to z less or equal to 2. Now, as the usual step, you can draw the normal curve and set the reason. So here is normal curve, and now you can see here at z is equal to 0, and you have to find for z equal to minus 2 up to 2. So minus 2 will be left side, z equal to minus 2, and z equal to here positive side. So you have to find out the area under this curve from minus 2 to 2. And this is very standard. So no tabular value is required because you are computing this is 2 sigma. This is 2 sigma range, which has total area around 95%. So your answer is 0.9544. This is the required probability here. So I hope you understand this particular problem. Let us now move to the next problem. So an electric firm manufactures light bulb that have a length of life is approximately normally distributed. So here it is given as the life of the light bulbs is normally distributed with mean equal to 800 and deviation is 40 hours. So you have x is following normal with mean mu and sigma square, where mu is given as 800 and sigma is given as 40 hour. Now sample, find the probability that a random sample of 16 bulbs. So remember that 16 is a not a large sample, but here the population is normally distributed. So we can apply central limit theorem to compute the average life of the bulb which is less than 775 hours, the probability actually. So here n is equal to 16, which is small, but because population is normal, so there is no problem. The sample mean x bar will be normally distributed with mean mu and variance sigma square by n. So now let us compute here what is the mu of x bar equal to same as the uh, population. So it is 800, and then standard error or deviation of x bar, which is sigma by root n. So here sigma is 40 divided by root of 16, which is 40 by 4, which is 10. Now what we have to find? We have to find out probability that random sample of 16 bulbs will have an average life of less than 775 hours. So we have to compute an average life, not the life of a bulb. If it is life of a bulb, this problem is reduced to the problem of normal. Perhaps we have covered this particular problem in our previous video lecture, which was based on normal distribution. So here it is asking average life. That means we have to compute x bar is less or equal to, or you can write it strictly, 775 hours. So this you have to find out. So now we have to change this in terms of Z, and then we can calculate the required probability by using the Z table or by standard curve properties. So when x bar is equal to 775, what is Z? This is given as x bar minus mu of x bar divided by sigma of x bar, which is standard error. So this means we have this 775 minus mu of x bar, which is same as population mean. So 800 divided by 10. So you have given as this is minus time 25 divided by 10. So minus 2.50. So your Z value here is minus 2 point. So this implies Z equal to minus 2.50. So this means problem of finding x bar average life is less than 775 is now changed to problem of finding Z is less than minus 2.50. So we can see here by the normal curve, we have this mean here 800, and this normal curve I can draw roughly like this, and Z is less than minus 2.50, so which will be around the left side somewhere here. So this is Z equal to minus 2.50, and I can draw the reason we want area which is less than this. So this particular area I have to find out. So what is this particular area? We have to compute from the table. So we want tabular value, that is phi of 2 minus times 2.5. And this value is given as 0.0062. And this means this area is 0.0062. And why this normal curve is required if you are solving the problem? Once you draw the normal curve, you can visualize whether your answer is correct or not. So like this cannot be 0.62. This area cannot be 0.62 because it is saying from figure total area left side is 0.5. This is very smaller. So we can guess how much the answer could be. It cannot be more than 0.5. So I hope you understand this particular problem. And we have next Problem number 3. A survey found that American family generates an average of 17.2 pounds of glass garbage each year. Assume that the standard deviation of distribution is 2.5 pounds. Find the probability that mean of sample of 55 families will be between 17 to 18 pounds. So mean of sample of 55 families. So this is given as n equal to 55. And you have to compute the probability that this 17 less than or equal to x bar less or equal to 1/8. And then you have on population side, it is not given as the distribution population is normal, but sample size is large enough. So you can apply Central Limit Theorem. And this mean is given as 17.2, sigma is given as 2.5. So you can compute what is mean of x bar. So E of x bar equal to mu of x bar equal to 17.2, and standard error of x bar, which is sigma of x bar, is equal to sigma by root n. Sigma is a population, so 2.5 divided by root of 55. So you can do this computation, and then you can apply central limit theorem to compute the required probability. And your answer here is this probability of 17 less or equal to x bar less or equal to 18 is equal to 0.71 around. So I'm not solving here. You can try yourself and you can find out this probability. So let us summarize overall uh, what we understand with this video lecture. First point is that whenever a population is normally distributed with the mean mu and variance sigma square, this implies the sample mean is also normally distributed with mean mu and variance sigma square by n. And this means E of, that means mean of sample mean is equal to mu, and standard error of x bar is equal to sigma by root n. This is very important to understand. And secondly, what we have seen using central limit theorem, when x bar will follow normal with mean mu and variance sigma square by n, and then this will directly imply, because x bar is normal, so we can use z as standard normal variate, that is x bar minus mu divided by sigma by root n. So this particular variate will follow normal distribution with mean 0 and variance 1. And so hence we can calculate, we can use Z table or the normal probability curve to find out the probabilities of x line from certain value x1 bar less or equal to x bar less or equal to x2. Okay, so it is a similar kind of problem as we have done in the normal distribution. And third point is very, very important here. So whenever your population is normal, we can apply CLT without worrying about the sample size. But if population is not normal, we can apply central limit theorem provided n should be greater or equal to 30. So this is all about in this video lecture. I hope you understand the sampling distribution and central limit theorem. Thank you all. See you in the next video. Thank you.